In Piazza Post 340, Matt asked, how do you calculate probabilities from z-scores? First off, you need to know what the distribution is to calculate these tail probabilities. So here we'll just talk about a normal distribution. So you assume that you have a random variable and it's normal. So this means it's a normal distribution with this mean and this variance. So the square of the standard deviation is just the variance, right? So this looks like, if you were to plot x, it would look like this, right? So if you were to plot x, it looks like this. The middle, the mean is mu, and the width is sigma, right? So this is the distribution of x. This is the PDF for x. So you want to know, given you have a z-score, given you have a z-score, you want to calculate some tail probability. So what does that mean? So if you have a point little x here, let's say you want to calculate the probability big X greater than or equal to little x. So you want to calculate the probability mass in this entire region here. So you want to calculate, you can think of it the integral along the PDF or the total mass larger than or equal to x. So you're told first off get a z-score, right? So why do you get a z-score? We don't know, but for some reason you compute a z-score little x minus mu divided by sigma, and then you take the z-score and you plug it into a function and it works. So what's the motivation behind this? So what is a z-score? So we have this over here has mean mu, which could be, let's say this is 0 here. It could be larger than 0, it could be below 0. It doesn't have to be at 0. And the width doesn't have to be 1, it can be any width, right? So what a z-score does is maps this point here. So you have this point on this distribution which doesn't have unit width and it's not necessarily around 0. And it maps it to a point on the standard normal. So the standard normal is here. So the standard normal has width 1. So sigma, let's call it sigma prime, is 1. And the middle, the mean of this standard normal is 0, right? So a z-score maps a point here to, let's draw this all the way, to a point, to the corresponding point on, let's call it x prime on the standard normal, right? Actually, let's call this z, right? Z for z-score. So given any let's say we're talking just about normal distributions. Given a normal distribution which is at some location, not necessarily 0, and it has some width, which is not necessarily 1, we want to map it to a point, the same looking point on this standardized version. And then we know all of these properties of the standard normal. So we have this function phi, we have a bunch of functions, right? So phi of x, let's say z. Let's use z here. So phi of z tells us for the standard normal, the probability, let's call the standard normal distribution, let's call it big Z. So it tells us the probability big Z is less than or equal to little z. So this phi function here tells us this probability. It tells us the probability for any point along the standard normal. It tells us the CDF. It's the probability mass before that point. And we have another function called Q, which tells you the probability big Z is greater than or equal to little z. Greater than or equal to doesn't matter in this case because it's continuous and it's smooth, right? So it doesn't matter. So here, this would tell you, this is kind of small, so we'll draw it again. Q tells you, you have this little z here, it tells you the probability of being larger than or equal to this little z. So from this you can see, what's the probability that you're smaller than or equal to or larger than or equal to? Well, that's going to be 1. So you have phi, you have this property plus q of z equals 1. So if you get phi, you can get q, and if you get q, you can get phi. They're just like one minus the other. So phi is 1 minus q, q is 1 minus phi. So you can pick one of them and use that. But anyway, so the idea here is you start with a point on any normal distribution. It doesn't have to be standard. It could be like here, it can have a different width. you map it to a point on this standard normal, you calculate the probability on the standard normal, and that corresponds to the probability on this. So let's say we want to calculate this probability here, going back to it. We mapped it to the standard normal. Let's neaten this up. We mapped it to the standard normal. So it looks like this. This is the standard normal. We map it to this point here. So what we could do is we could calculate this probability here in the standard normal after we've mapped this point to the same point on the standard normal. And then we can calculate this probability using Q. So this is exactly Q. So what have we done here? We have Z. Sorry, this is Z. So we have Z equals this. And if we want to calculate the probability, big X is larger than or equal to little x, this is going to be Q of Z. That's it. So we take this X, we turn it into Z, and then Q of Z is the probability, is the right side probability. So you can write this down, but it's easy to remember. Phi is to the left, Q is to the right. Somebody arbitrarily decided that. You could just as well calculate the probability X is less than or equal to X. So big X, the random variable, is less than or equal to this X. So you could calculate this probability using phi. So just get the z-score here, and then calculate phi of little z. That's it. So if you want to calculate something like, if you have a distribution, and you want to calculate, let's say, this is the mean, and you want to calculate the probability of being, let's say, 5 away from the mean. What's the probability of being 5 away from the mean? Well, that's this probability plus this probability, right? But because the distribution is symmetric, it's just 2 times this probability. So 2 times this probability, well, how do we calculate this probability? So just take, get the z-score. So the z-score here would be z equals, this is mu plus 5. This point here, x is mu plus 5. Mu plus 5 minus mu divided by sigma. And this is just 5 over sigma. So we can get the z-score corresponding to this point, calculate the right tail. So the right tail is this thing over here. So that's Q of z. And so these two tails, the area under that curve is just 2Q of z, where z is this. So it's 2Q of 5 over sigma. So that's the idea. And then ERF is this other function that I could discuss later if people have questions about it, I guess. But you can get away with only using phi and q for most of the problems.